Good afternoon, everyone. Write your complete enrollment number in chat box. All the students write your enrollment number. Now we start the unit 2, the last two topic, that is refinements and iterative deepening. So in game theory, the last two topic is remaining. Already we have covered the topic game playing, Minimax search algorithm, and alpha beta procedure, right? Now the last two topic, that is refinements and iterative deepening. So I hope you have cleared the concept of Minimax and alpha beta procedure. Okay. Now we start refinements. What is refinements? So refinements, in addition to alpha beta pruning, there are a variety of other modification to the Minimax procedure that can also improve its performance. Already we see in Minimax algorithm, we are change and we use the we produce a alpha beta procedure, right? So we utilize our time compared to Minimax algorithm, right? So there are the different also possible changes that improve your efficiency of your program, that is your refinements. Okay, so how, what are the changes you can make for improve the accuracy and improve the result of your program? So first one is waiting for quick scenes, means continue the search until no drastic change occur from one level to the next level. So these are the some of the trick that used to improve your efficiency of your program. The second one is secondary search. So after choosing a move, search a few more level, benefit it to be sure it still looks good. And the third is using book moves. So for some parts of the game, keep a catalog of best moves to make. So you have to choose always best move. Okay, so this is your third. And the last is alternatives to Minimax. So we see the next topic, this is your iterative deepening. So you have clear what is the alternative of Minimax algorithm and how we can improve the result of your game playing example. Okay, so these are the four trick that is used to improve your performance of your system. Now we start the main topic, that is your iterative deepening. Okay, all are audible?
Yes, ma'am.
Okay. Now we start the main topic, that is your iterative deepening search. So this search is also called as a iterative deepening depth first search. Okay, these two names are alternatively used for this technique, that is your iterative deepening and search. Okay, so we clear one by one, we see how this algorithm works. Okay, so start with the first. So you have already know the major two search technique is BFS and DFS, right? There are the two common ways to traverse a graph, that is BFS and DFS. Considering a tree of huge height and width, both BFS and DFS are not very efficient due to the following reason. You already know the advantages and disadvantages of BFS and DFS. Sometimes it not provide good result because there is a long length of your tree, and sometimes they not provide the guarantee or complete answer of your system, right? So DFS first traverses nodes going through one adjacent of the root, then the next adjacent. The problem with this approach is, if there is a node close to the root but not in a first few subtree explored by DFS, then DFS reaches that node very late. Also, DFS may not find the shortest path to the node. Okay, DFS give the answer, but that not provide the shortest path, because suppose you have a given tree and you have a find this is your 2 number is your goal state. So in DFS, you have to go in the depth, right? So you are starting with your root node, then you are going the child of root node, then also go in the depth of this node, right? So sometimes it is near to the directly root node, but it takes times to find your goal state, right? So some of the few disadvantages of DFS. So here you can see, suppose we want to find a node 2 of the infinite undirected graph, a DFS starting from node 0 will dive left towards node 1 and so on. So whereas the node 2 is just adjacent to a node 1. Hence, a DFS wastes a lot of time in coming back to the node 2. An iterative deepening depth for search overcome this and quickly find the required node. So we built a new algorithm that provide the advantages of both BFS and DFS. You can see here the 2 is near to the address of A1, but they find the different path and then they find the goal stored. So it takes lots of time to compute your answer, right? But in iterative deepening search, you can search level by level. So first of all, we see what are the advantage and disadvantage of DFS, BFS. Then we come to this topic, iterative deepening search. Okay. Now, what is the benefits and overcome of this BFS? So BFS goes level by level, but require more space because the space required by DFS is D. Where D is the depth of the tree, but space required by BFS is N, where N is the number of nodes in the tree. Asymptotic notation आपको पता है, right? ये big O. So you can consider your time and space complexity in terms of asymptotic notation. This is your big O. Big O and under D. This is your complexity of BFS. And note that the last level of the tree can have around n by 2 nodes and the second last node have n by 4 nodes, and in BFS we need to have every level 1 by 1 in a queue. In BFS there is the disadvantage is they require a more space to explore your path, right? And in DFS it takes a long time to find your goal state. Suppose it given in edges of your root node, right? So these are the two pitfalls of BFS and DFS. Now we come to the topic, iterative deepening search. Okay. So also is called as the IDDFS, combined depth for search, space efficiency, and breadth for search, fast search. Okay. So already we see the DFS takes more time compared to BFS, and DFS require less space compared to BFS. So we consider both the algorithm advantage, like DFS search space efficiency and BFS is a fast search, right? So we combine these both the properties in iterative deepening search, means IDDFS. Okay. So how it's work? So IDDFS call DFS for different depth starting from the initial level. In every call, DFS is restricted from going beyond given depth. So basically we do DFS in a BFS fashion. So how it works? So I give one example so you have clear. This is your algorithm for IDDS. First we clear the concept, then we revise algorithm. So you have more clear this algorithm. So an important thing to note is we visit the top level node multiple times. The last level is visited once. Second last level is visited twice and so on. It may seem expensive, but it turns out to be not costly. Since in a tree, most of the nodes are in the bottom level. So it does not matter much if the upper level are visited multiple times. Okay. Now we take one example so you have clear. First of all, you can see here how deepening, iterative deepening search. So you have given a tree or a graph that are two types. The first one is when graph has a no cycle, and when the graph has a cycle. So cycle means the all the nodes are linked with each other, so there is no separation or the separate path for traversal, right? So cycle, they make a cycle means all the nodes are connected with each other. So when the graph has a no cycle, so this case is a simple. So we can DFS multiple time with the different height limit, but in cycle, this is interesting as there is a no visited flag in IDDFS. So we take this example, so you have clear. So all are visible this graph?
Yes, ma'am.
Okay. So starting with how the iterative deepening works. Okay. So you can see here you have given a graph because this is your graph that have a cycle. You can see here 1, 0, 4 and 5 is connected with each other. So there is no separation between two nodes. So this is called as a cycle. Okay. So here we take this example when the graph has a cycle. This is a very easy. Suppose here the edge is not given, then it is the when the graph has a no cycle. But this is a complex example, so you have clear. So first of all, what you have to do? First of all, you have to give the level number. So this is your root node, right? So level 0, then level 1, then level 2. Same as it is, there are n number of lanes, so you have to give the number of all the level. Okay, clear? This is your first step. Now, this algorithm provide the benefits of both BFS and DFS, right? So how it works? So we have to explore the node level by level. Means in BFS, we are visit the node 0, 1, 2 and 4, right? And in DFS, we are visit the node 0, 1 and 3. But we have to combine the features of DFS and DFS. Means start, suppose at level 0, suppose you have to iterate level by level. First of all, you have given level 0. So what is your output means 0. Means you have to now increment the level 1. Now what is your output? 0, 1, 2 and 4. So we are going the depth. So this is your DFS and we are visiting the node means same as it is as a BFS. So we provide the features of DFS and BFS. Now the next level we increment the level 2. Now how you can explore? So 0, 1, 3, 5, 2, 6 and 4. Means you have to increment a level. So you are going the depth and visit the all the child of this node, then explore 2 and then their child 6 and this is your 4 and explore their child 5 and 1. Okay. So how it works? So I give in a more generalized way. You can see in this table. So how you have to solve this example? First of all, you have to make a table. So you have to write depth 0, 1, 2 and 3. First of all, you have given this graph and you are exploring the level 0. So you have explore only one node, that is your 0. Means iterative deepening depth for search. How it explore all the node. Now at level 1, so you are given the level 1 has a 1, 2 and 4. So you are first of all you have to go in the depth. So means they provide the functionality of DFS. So 0, then 1, then 2 and 4. Okay. Now at level 2, you can see here 0, 1, 3, 5, 2, 6, 4 and their child is 5. Okay. So this is your level 2. Clear? If you have doubt, then you can ask me. Here you can see, so at depth 0, you have one node, so you are exploring 0. Now level 1 has a 3 child. So you have first go in the depth and then you have visit the level 1. So you are visiting 0, 1, 2 and 4. Now you are comes to the level 2. So you have 0, 1, 3, then their child other 5, then you are comes to this 2, their child is 6, then 4 and their child is 5. Okay. Now at level 3, due to this limitation, I not added this nodes child. So you can see here there has also one child. So at level 3, 0, 1, 2, 4. So first of all, starting with the node 0. So 0, then 1, then 3, then their child 5, then 0 has a 2 and their child is 6, then 4, 4 has a child 5 and 5 has also link with 1. So you are writing at 1 because this is your level number 3. So you clear the difference between level and how to node explore. So at level 2, you are exploring till your node 5, right? But this is your level number 3, means your depth is up to 3. So you are exploring this one also. So starting with 0, you are comes to this. Again I repeat. So you can see here at depth 3. So starting with 0, you are exploring their child 1. Yeah, 1, then their child is 3, then 1 has a child also 5, so 5, then again 2 and their child is 6, and 0 has also the other child 4 and their child is 5 and their child is 1. So this is your iterative deepening search example, that is a combination of BFS and DFS. Clear?
Yes, ma'am.
Now I give one example. You have to explore the path and give me the final path. Okay. So start this example and give me the path how you can visit this tree at level number 3. You have to find a path using iterative deepening depth first search and give me the final answer at level number 3. How you can visit this tree? All the students write your answer in chat box. So starting at level 3, how you are exploring? Using iterative deepening depth for search. So you are starting with A node, right? Now you are exploring their child B, then D, then H, right? Now D has a second child, that is your I. Now B has a child, that is your E. Now you are comes to the next C. Then C has a F, K, and last answer is your G. Okay. All the students have clear. So what is your answer? A, B, D, H, I, E, C, F, K, and G. Now I give the second example. You have to explore, or your goal state is your R, right? So how many number of nodes you have to require before R? So you can tell me. So you have to find the 8 level depth 4. Your goal state is R. So how many nodes visited before reach to your final or goal state?
Six.
Which six? So you can give me the path. So starting with A node.
A B E I C G L R.
Uh, no, F node already you are not visited because B node has a two child E and F, right? So first of all you have to also explore F node. Then
Okay,
that
okay,
comes to the C.
okay.
So then you can give me the answer. Now you reach to your R state. Then one by one, starting with A node. Write your answer in chat box. So I verify your answer. Yes, some students have write their answer. Now we check. So first of all, they start with the root node, then comes to their child that is your B. Now the B has a child E. Then E also explore their child I. Now B has a second child F. F has a two child J and K. Now K has a two child O and P. Now we are backtrack here. You can see. Now we are comes to the A because there is no goal state available in this exploration. Now we comes to the A. Then again we are exploring the next child of A is a C. Now we come to the next child of C that is C, G, then L and R. So how many child we require to explore? A, B, E, I, F, J, K, O, P, C, G and L. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So total 12 node we are exploring before reach to your goal state, starting with your initial state. Now you can understand we are visiting this layer two times. You can see. So we are starting with B node, E and I, right? So again we are backtracking and then we are exploring this node twice, right? Same as it is, we are visiting this node three times. So we can calculate the complexity or time complexity of this algorithm because we are starting with here, we are going the depth and then we are again backtrack, so we are again visit this node. So only these leaf nodes are visited only once. Then the third layer is visited more than this leaf node. Then also this depth number 2 is visited more than this depth number 3. And also this depth number 1 is visited more than this 2, 3 and 4. Right? And also visit this depth is equal to 0 more than this all this below level. So we can calculate the complexity of this algorithm. So how we can calculate all our so So you can see, first of all, what is time complexity? Suppose we have a tree having branching factor b and its depth d. So there are the b raised to d nodes. So you can see here, you have given a branching factor, means the node number of nodes in a tree, right? So suppose here is a branching factor 3 and the depth is your 4. So b raised to d is your time complexity. In an iterative deepening search, the nodes on the bottom level are expanded once. Those on the next to the bottom level are expanded twice, and so on, up to the root of the search tree, which is expanded d plus 1 time. So the total number of expansion in an iterative deepening search is, you can calculate using this manner. D is your depth and B is your branching factor, right? So already we see this depth level is visited only once. Then we are visiting this twice and thrice and so on. We are visiting this also level, right? So we can calculate using this manner, d into b plus d minus 1 into b square up to this is your root level. So that is summation. We can sum these all the terms and we can find which is your big O b raised to d. So after evaluating the above expression, we find the asymptotically IDDF has takes the same time as DFS and BFS, but it is indeed slower than both of them, as it has a higher constant factor in time complexity expression, because the complexity is same as it is BFS and DFS, but it has a fast computation because there is a more constant terms. So constant has a direct simple value. Suppose there is a variable, so we are finding the value and then we are evaluating the expression, right? But here the more number of constants, so we are the IDDF has a fast computation. So but it is indeed slower than both of them, as it has a higher constant factor in the time complexity expression. So IDDFS is a base suited for complete infinite tree. When you have a given graph has a more number of layer, then it is a very useful algorithm for find your path. Okay, so now we are compare BFS, DF and IDDFS. Okay, so all are visible this table.
Yes, ma'am.
So starting with DFS and BFS, you are already studied this topic. So the time complexity is B raised to D, and space complexity of DFS is a D, and BFS is exploring all the nodes and that save in the queue. So that takes more time. That is your B raised to D. So, but it is a fast compared to DFS. So we take the both the advantages of DFS and BFS, and we are making this IDDFS. So you can see here the space complexity of IDDFS is a B into D. Okay, so we reduce the space and utilize a more time. Okay, so you can see the time complexity of DFS is B raised to D, and BFS is also B raised to D, and IDDFS has a B raised to D, and space complexity of DFS is D, then BFS has a B raised to D, and IDDFS has a B into D. Now, when to use? So don't care if the answer is closest to the starting vertex and root. When graph entry is not very big and infinite, that's why we are using DFS. And when we use the BFS, when space is not an issue, because BFS takes more space. So if you have a lots of space available, then you can use this BFS algorithm. When we do care, want the closest answer to the root, so that's when we are using BFS. Now, when we use IDDFS, so you want a BFS, you don't have enough memory and somewhat slower performance is accepted, then you have to use BFS plus DFS, that is your IDDFS. Okay. Now, so you can see here, what is completeness. Sometimes these terms are mostly used for finding or the performance finding of your algorithm. So what is time complexity, completeness, space complexity, and optimality? So a search strategy is defined by picking the order of node expansion. So search strategy are evaluated along the following dimension. The first one is completeness. So what is completeness? Does it always find solution if one exists? मीन्स आपके पास एक ट्री है, उसमें आपका गोल नोड है, तो कंप्लीटनेस किसको बोलते हैं? जो भी एल्गोरिदम है वो एनी कंडीशन में आपको फाइंड करके देता है. वो ज्यादा मेमोरी भी यूज कर सकता है और टाइम भी यूज कर सकता है, बट दे गारंटी टू प्रोवाइड अ सॉल्यूशन. So this is your completeness. Now the second term is time complexity. So number of nodes generated means they takes the time to generate a number of times. So this is your time complexity. Now the third is space complexity. So maximum number of nodes in a memory is your space complexity. And what is optimality? Does it always find a least cost solution? Means आपका जो algorithm है वो solution तो provide कर रहा है, but it provide a least cost means मिनिमम टाइम्स कॉम्प्लेक्सिटी एंड मिनिमम स्पेस कॉम्प्लेक्सिटी में जो भी आंसर आपका एल्गोरिदम दे रहा है उसको बोलते हैं ऑप्टिमलिटी. ओके, व्हाट इज ऑप्टिमलिटी? डज इट ऑलवेज फाइंड द लीस्ट कॉस्ट सॉल्यूशन. नाउ यू कैन सी time and space complexity are measured in the terms of B and D. So what is B? So maximum branching factor of the search tree. So means you have a root node and you have a 3 child. So branching factor of your tree is a 3. And what is your depth? So we are already marked depth 0, 1, 2, 3. So depth of the least cost solution. And what is M? So maximum depth of the state space is called as a M. Sometimes maybe it is infinite. Okay. So these all are the terms that is mostly used for evaluating a search strategy or search algorithm. Now you already solved the example of iterative deepening. So you have cleared this algorithm starting with your IDDFS. You are given a source, target, and maximum depth, because here you are using a limit of your level explorer, right? One by one you are increasing the depth. So at level depth number 0 you are visiting node, then you are increment depth plus 1. So that is plus means depth of 1. Then you are increment 1 level, depth 2, and you are check if it is exist, not exist, then you are again increment the depth. So you will give the limit of your depth and target. What is your destination? So for limit from 0 to maximum depth, if DLS source target limit, then it is available, then directly return, right? Then if limit less or equal to 0, and then return false. If it is not available, then the return false. And you are adjust this all the node and return true. Okay, you are exploring this example, so you have clear. Anyone have still doubt in today's topic, then you can ask me a question.
Ma'am, what is the completeness of IDDFS?
Completeness means you are using the so you are using the advantages of BFS and DFS, right? So BFS yes, provide the guarantee to find your solution. Somewhat that takes the more memory. So here iterative deepening search always provide your completeness answer. Means you are increasing the level by level. At last level, suppose you have a node or your goal state, then provide a solution. So this is a complete, it provides the completeness.
Okay, and will the answer always be optimal, or it depends?
No, sometimes it provide optimal, sometimes it not provide optimal.
Okay, so in BFS we will always have the optimal answer, but in IDDFS it depends.
Yes, you can see here the complete, then it is a yes. The time is b raised to d, space is b raised to d, and optimal, yes, if step cost is equal to 1. Here they provide the condition. Okay, sometimes what happen, you have a given cost of all the edge have a different cost of your edge, right? So that time we are not say guarantee that this is your optimal answer. Suppose you are taking exploration of all the edges that cost is uniform, then it will provide the optimal answer.
Okay.
Okay.
So in in finding shortest path in maps or some trees with weighted branches. So in that scenario, it might not provide the optimal solution because we have different weights
Huh.
for different branches.
Yes, but because we are not have a uniform cost, because
Okay.
that's why they not provide uniform optimal. But
Okay.
mostly, if you have a uniform cost, then it is the provide optimal answer.
Okay. And one more question is that when we calculate the time and space complexity, where we have b equals to the maximum branching factor. So suppose we have a tree where
Hmm.
we have put around 1000 branches, and
Hmm.
out of the 1000, there are uh, there are a few nodes. Most of the nodes have only two branches, but there's only one or two nodes which have three branches. So
Hmm.
do we take two for the value of b, or we have to take the
You can
number three?
you can see here if the f number 0 you have a branching factor this, so you have to write in this manner because you are sum all the term individually. So at d minus 1 level, what is your branching factor? Your d minus 2 level, what is your branching factor? So you have to calculate d minus 1, d and all. So separately you have to calculate individual term, then all the summation of all the terms.
Okay.
Yeah, level
So
by
when we
level.
write b raised to d, it's just a it's summation of all the nodes having different branches. So it's not a general
Yes.
purpose. We have to calculate it for every node. So it's like a long equation. We just
Ha,
write it
yes.
in short only.
Yes, you are studying, I think, computer algorithm subject.
Yes, but we didn't study these Lego notations, etc. We just had
Okay.
general
This is the main
overview.
important theory for your finding your complexity. This is
Yeah.
that takes 2 or 3 lecture for explanation how you can calculate, and final you are writing d raised to d, because
Yes.
you are sum all the level by level, and your general terms you can use that provide the big o, that is your maximum probability. Here big o is used for maximum value of your complexity. There
Yes.
are there are 5 notation: big o, small o, then omega, and small o, big o same as it is small o, and big omega same as it is small omega. So there are the 5 terms used for finding the complexity.
Okay.
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 Anyone
Thank
have
you.
doubt? Yeah. Are you satisfied with my answer?
Yes, ma'am.
Okay. If you have any question, then ask your question. I take the attendance. File number. First of all the students write your enrollment number. 5, 9, 11, 31, 6, 18, 36, 37, 23, 8 number, 16, 29, 41, 34, 6 number, 1 number, then 46, 39, 32, uh, 1 minute, 42, 45, uh, 25, then 2 number, 40, then 20, 19, 21, 22, 33, and 43. Anyone still left? 24. Already 24 is present. Okay. Anyone left? Then you can write your enrollment number first in chat box. If you have any doubts regarding any previous topic, then you can ask me a question, and I uploaded all the lecture video in YouTube. So if you require the revision, so yeah, at the exam time, so you can use this my channel, YouTube channel. That in that I created a playlist that is your subject artificial intelligence. So you are attending this lecture, so you have easily understand all the topic and you are revised the content. Okay, I hope you have liked this channel, so please like, share and subscribe for latest video notification. And if you have any question regarding theory, then you can ask me anytime.